So there are going to be three major differences. The first is that the books are here now. The second is that we're going to have green light here rather than that. And the third is that we're going to talk about animals. Yeah, thank you very much for organization and for inviting me. So I'm in UCL, and these names that you see down here are the places where I either performed the experiment or did data analysis of the work which I'm going to show now. I'm going to start, hopefully this will work, by briefly talking about this paper which came out around 12 years ago. And this is a review paper in which authors are basically summarizing their own work and many other people in the field, and about the experiment that they did in a variety of species, from human to dolphin, monkeys, pigeons, and rodent, with the aim to basically evaluate the metacognitive ability across these species. And given that this paper is coming in this amazing behavioral and brain sciences, it comes with this large open commentary from many people in the field. And then looking at sort of this massive paper with all these comments, it looks like a debate about whether we should actually grant metacognitive ability to animal or not is something that people cannot apparently agree on. This is something, open question that I think is still basically a matter of more research. But looking at this sort of conclusion that the paper has, there are two things that I think people implicitly or explicitly agree on. The first is that regardless of granting metacognitive ability to animal or not, it looks like that many of the experimental animals might have at least part of the machinery or brain structure which might be used for solving some sort of metacognitive tasks. And this is good news for sort of electrophysiologists and system neuroscientists, because then we have this precise and basic method, and we can tap into those sort of machinery and understand the sort of neuronal computation. The second sort of conclusion that people kind of agree is that when we talk about metacognition, we can probably approach this question by using simple normative sort of models that would allow us to define our variable sort of in a precise way and hopefully try to avoid semantic issues. And when we think about decision confidence, which is basically the particular focus of my talk, this idea of sort of computational approach is quite intuitive. Against the idea that confidence is a metacognition sort of ability, when we think about confidence, we can also think about sort of simple computation that we do in a statistic when we basically evaluate the hypothesis and we generate p-values. And this is essentially the approach that I'm going to take. I'm going to basically show a couple of examples from behavioral and neuronal data in which we try to basically take approach to better understand the animal behavior and the activity of single neurons. So yeah, with this introduction, the outline of my talk will be the following. Essentially, I will start with introducing a behavioral task, which is used for estimating decision confidence in rats. Then I will show a simple model which can be used for relating behavioral report and decision confidence. Then we compare rats' behavioral report and decision confidence. And then we think about the role that orbitofrontal cortex might have in this sort of computation. Then we will switch the species and we will switch the brain area. We go to dopamine system. We look at dopamine system in monkeys, and we try to build a reinforcement learning model which takes the confidence into computation, and then we compare dopamine responses and sort of the prediction of our confidence-dependent RL model. So thinking about behavior, so we started with this very well-studied sort of paradigm, which is odor-guided decision-making in rats. So these animals are thirsty, they want to get reward, and they are sitting in the box for like 1 hour per day, and they are trained to essentially make a sampling here and the odor sampling here, and then based on the identity of odor, they either go to the left or right, and if they're correct, they will get a liquid, a drop of liquid. And given that they are thirsty, they will do that for like hundreds of trials per day. Given that these animals are really good in this sort of categorization, then if we do that basically with very simple pure odor, like which we are showing here, then the performance of the animal is really good. They are not making mistake, almost not making mistake. And these are not really the trials which are useful. If we want to think about confidence, then we need to have sort of situation that animals actually making mistakes. So, and we do that by pushing the animal and introducing sort of odors which have like a mixture of both odors. And when those odors are introduced, then the performance of the animal, as you can see in this psychometric function, which I draw with my hand, you can see that basically, yeah, they are making sometimes errors, sometimes they are correct. So the psychometric function looks good for our, essentially our purpose. So with this basically basic task, then we try to basically satisfy two things. We wanted to change the task so that we can collect both choice and a measure of confidence on the same trial, and ideally we wanted to have a measure of confidence which is on a continuous scale rather than a binary bet. So we changed the task as following, which I'm going to go basically through the steps of the task. Once again, animal is starting by doing the central nose poke. Animal would receive a mixture of odor, and after that he would either jump to right, left or right. Animal is either correct or incorrect. We don't immediately give the reward. Animal is actually waiting a little bit here for reward, and the reward delivery schedule is essentially following an exponential decay with some constant, and which is basically up to 8 seconds. So if the animal is wrong, then you would essentially wait here a little bit, you would not get the reward, and you would essentially start the next trial. If the animal is correct, at some point with some delay, he would get the reward. But crucially, in some of those trials which are correct, although animal is being in the correct choice board, they are not delivering the reward. And these trials are basically catch trial or reward omission trial. And now we end up having basically two types of trial in which animal did not receive the reward, some of them being correct and some of them being error. And the reason that we are basically introducing this catch trial is that given that we are interested in the waiting time of the animal, we cannot really measure waiting time in this rewarded trial, because as soon as the reward is coming, the animal will start basically consuming the reward, and it would stay to basically collect the whole reward. So we basically then look at the waiting time of the animal in these two types of trial, and also animal choice. So some basic of the behavior, again, psychometric function look good. They are basically here fit on different sessions, and thus are basically average of whole session. If you look at odor sampling, duration is largely flat. It's showing a mild dependence on the contrast of the odor. And here I am essentially showing the distribution of waiting time from one animal and the water delivery schedule. That will be that exponential delay, and that will be later important for understanding our model. So, thinking about the task and waiting time, it's probably intuitive to think that waiting time is probably reflecting the animal's confidence in the task. Like when animal is sure, then he would tend to stay longer because he knows that he's correct and reward will come. If animal is less sure, he would more probably leave the choice board quicker and start another trial. But then we try to basically to be a little bit more principled and try to connect this to basically variable using a bit of simple model. So to think about that model, sort of, when the animal is essentially in the choice board, so he has made a choice, he's staying in the choice board, and he can basically, at any moment in time, the animal can do two things. Either he can wait for another second or another moment, or he can leave and initiate another trial. And in order to perform this sort of moment-by-moment comparison, what animal would do is basically comparing two different things, value of waiting versus value of leaving, or opportunity cost. So, and then the idea is that as soon as value of waiting is below the opportunity cost, then animal should leave the board and start a new trial. And we can be a little bit more sort of formal about this, and then we can define WT as a sort of event that the waiting till time t has not resulted in reward. And then we can define R as the event that the reward will come in next moment in time. So in this condition, then the variable which is interesting for animal is the conditional probability of R given WT, which we can essentially write it using essentially this basically a framework. And this conditional probability, then you can see it depends on things. So the first one, the probability of waiting till time t, given that the reward will come in next moment in time, is the 1 by definition. Probability of reward would depend on different things. It would depends on the confidence of the animal. It also depends on the schedule that you define for the reward delivery. You remember that exponential decay. And when we think about the probability of waiting till time t, we can evaluate that as 1 minus the probability of being rewarded till time t, which again depends on confidence and reward schedule. And we can put these basically parameters into equation, and we basically end up having a function which basically reward expectation per time, which I'm basically showing in this sort of schematic. And then this is basically telling the animal how valuable it is to wait at any moment in time. And going back to this idea of comparison with opportunity cost, we can kind of consider that opportunity cost is a constant, which is basically this line. And in this framework, that the optimal waiting time is the place that opportunity constant or opportunity cost and this reward rate are meeting each other. And we can basically then rearrange the equation and solve optimal waiting time. And what we can see here is that the waiting time that we are deriving from the model is basically showing a monotonic relationship with confidence, and therefore can be sort of considered as an index of confidence. So far I didn't actually talk about how we measure confidence. We are just saying we basically call it C, and then the way that we did confidence is basically the signal detection framework, which Anna explained very well, so I'm not going to explain it much. Essentially, there would be a stimulus sample, there would be a boundary sample, and then the comparison between two samples would give a choice, and a calibrated distance between two samples would essentially generate decision confidence. For example, in this trial, the model would go right, and then this distance is large, so the confidence is high, in contrast to the other trial. So we then thought, okay, maybe we can actually play with these three parameters that we have in the model and fit the model on animal behavior. And we did that essentially by starting from animal psychometric function, and there we are essentially estimating a standard deviation, which is basically reflecting the amount of noise that the model is facing when it's making this categorization. From that standard deviation, we are basically going to basically estimating an intermediate variable, which is decision confidence, using our signal detection framework, and then we are estimating kappa, the opportunity cost, in order to minimize the difference between the waiting time distribution of the animal and what is generated from the model. And what you can see is that after this optimization, essentially waiting time in the model are doing a good job in replicating animal behavior. And now I'm going to go a little bit into the detail of the sort of features that these two parameters have. So the first thing is that we can essentially look at the psychometric functions. So here we are basically separating the psychometric function of both model and animal based on the duration of waiting time for that trial. There will be some trials which are long waiting time and some trials which are short waiting time. And what we can see is that in both model and rat, in the trial which the waiting time has been long, the accuracy has been improved. So the psychometric function is sharper. And the other feature is that waiting time can predict the accuracy, and that's the case for both model and the rat. And the third thing, which Anna showed, is essentially the correlation, the dependence of waiting time on both trial outcome and stimulus contrast. So what we can see is that when the animal is right or when the model is right, then the waiting time will increase, and when the model is wrong, the waiting time will decrease as a function of mixture contrast. So these are basically telling us that this sort of confidence-dependent waiting time that we measure in the model are doing a very good job in replicating the sort of waiting time behavior that animals show, and suggests that the waiting time that animals are showing can be used as the implicit report of decision confidence. But surely when we think about this waiting time, how much animal is actually willing to wait on every trial, it cannot be only depend on confidence, right? It basically can depend on many other parameters, like previous outcome or previous waiting time, or how late in the session animal is performing these tasks. And the question is, whether this sort of parameter can affect that sort of pattern that we saw before, right? And in order to give a taste about this, well, I'm just going to show the first parameter. And in this scatter plot, we are basically looking at the average waiting time of many animals. So each dot is basically one rat. And what we can see is that many of them, they are tending to wait a bit longer after a correct trial compared to error trial. And then now, if you look at one of those animals or two of those animals, then what we can see is that, for example, in this animal, which is highly affected by the previous outcome, the pattern that we have seen before is there. It just moves upward and downward, basically. This parameter is basically modulating the waiting time on this axis. And if you think about sort of this in the context of our model, these are the sort of parameters to me that they are essentially modulating the opportunity cost, the flat line that we showed, and if that line goes up and down, this will essentially create this sort of movement of the waiting, the movement of the pattern up and down in this scale. Okay, so now, yes?
Need that be the case? So you assume that it says this criterion on your waiting time that's getting adjusted based on past feedback? could it be that the constant signal changes?
Yeah, it can
Yeah.
be. Yeah, I'm just trying to simplify. I mean, just trying to basically say that sort of this reinforcement related sort of variables do have effect on absolute waiting time, but to a good degree, they are not affecting the pattern that we have.
Yeah, okay.
Yeah. Yes, I completely agree. One can make the story a little bit complicated. I actually, if saying that the past sort of parameters would affect the waiting time to the extent, to the sort of confidence to the extent that is reflecting in this pattern. But at the single sort of, at the simplest level of analysis, basically, it looks like that the pattern is robust. Yeah. So okay, now with this behavior, we try to essentially see what orbitofrontal cortex would do. And the reason that we are looking at orbitofrontal cortex is that there is a study from Alan Kepes and Zach Mainen, which they recorded the activity of OFC neuron in a sort of similar version of the task. The recording task didn't have the confidence report, but it's basically the same sort of perceptual categorization. And what they show is that these neurons do have a representation of decision confidence. So the question which is there is OFCs actually necessary for confidence judgment or not? Do we have a representation which is basically functional and it would basically affect the behavior of the animal? The second rationale for looking at OFC is the other study which has been recording from LIP, from Marshall and Ruzvikiani, and what they are suggesting is that the same single neuron, when they are recording from LIP, the same LIP neuron is reflecting both animal choice and the confidence that animal has in the correctness of the choice, which basically suggests a mixed representation of confidence and choice basically in the same sort of neural representation. And the question that we try to address is, do we have structures in the brain which have a representation of confidence without really having a representation of choice? So with this rationale, they started basically inactivating orbitofrontal cortex of this trained animal. So we do have cannulas on those OFCs, and on alternating days, these animals are receiving either mucimol as like an injection, which is a GABA agonist, or saline, which is basically a control situation, or nothing, which is again a control situation. So, and then we compare the performance of the animal in the control condition and in the mucimol condition. So looking at the psychometric function of the animal, what we see is that when we inactivate the cortex, OFC cortex, there is no effect on the psychometric function of the animal. There is also no effect on the average waiting time or other measures such as odor sampling duration or movement time of the animal. So this basically suggests that when the OFC is inactivated, animal is perfectly able to make the categorization. It goes correctly to left and right, and that's why we have overlapping psychometric functions. Looking at the waiting time pattern and then separating based on what we can see is that in control condition, for example, when we are looking at this the separation of psychometric function, what we can see is that in the control condition, we do have the separation of psychometric function when we are separating trial based on waiting time, but that separation doesn't work for inactivated sessions. When we look at this pattern that we saw before, what we can see here in the mucimol condition, that dependence on outcome and odor contrast is largely gone. And you remember that waiting time was predicting accuracy, and what we see in the control condition, and that dependence is also largely gone. And based on this analysis and other analysis, we essentially kind of think that orbitofrontal is necessary for this confidence-dependent waiting judgment. And essentially, this is basically telling us that given that the perception is not affected, the psychometric functions are overlapping, but the confidence behavior is affected, we think that OFC might have a second order representation in which the confidence is computed and presented, but sort of first order sort of variables, so that choice itself are not presented. So with this, I'm gonna do the conclusion of the first part. So we basically showed a sort of task which is useful for collecting choice and confidence from same trial, and we showed that waiting time can work as a continuous wager. Then we went to OFC and showed that OFC is necessary for confidence-dependent waiting behavior, and sort of in general conclusion, it looks like that the process of decision and decision confidence can be at least separated in some part of the brain. If you have questions.
Yeah. So it's just what part of your so is it the case that the reward accumulated across the experiment is different when they receive the experimental treatment? Because it looks like the behavior is different, but I don't know if actually the effect.
Yeah. No, it is not. So that's a good question. One can really go to the detail of that. The simple analysis that I did in terms of how much reward they collect at the end of the session shows that they are collecting the same amount. But that is not a well-controlled thing in my experiment because I simply sometimes take an animal after 1 hour or after 1 hour and 3 minutes. So that's one thing, and it might be the case also that I'm not really controlling for the exact time that I'm putting the animal in the box. It might be in the morning, it might be in the afternoon. They might have different behavior about that. They might be like thirsty with different levels. So I didn't go through the detail of that. But my simple sort of t-test analysis is showing that they are getting more or less the same amount of
because it could be it affects some strategy rather than some representation.
Yeah. Well, I don't think it's likely to be the case because given that they are doing these many trials and basically collecting, most of the days they're collecting actually more than what they need, I don't think the sort of the accumulated reward can explain the pattern that we have. Okay. All right. Now we're gonna go to dopamine neurons in monkeys. So when we talk about dopamine neurons, these are essentially neurons which are located in ventral tegmental area and substantia nigra. And when these neurons are active, they are releasing dopamine in downstream structures. And these dopamine neurons are heavily implicated in sort of reward learning and decision making. And the main hypothesis about this neuron is the idea of prediction error, basically, that I try to explain in this graph, which you have probably seen several times. So here we are looking at the activity of one single neuron, which is close to a wire that we are basically using to record, from a monkey which is sitting in the dark, and the monkey is thirsty and looking at the monitor. Right. So here in this condition, animal is suddenly receiving a drop of juice without any expectation. And what we can see is that the activity of the neurons are showing some modulation. These dots are basically individual spikes, and here you are basically putting all of them together. Right? In this other condition, we are basically looking at the experiment in which animal has been previously trained to associate one visual cue to reward. And what we can see is that at the time of this reward predicting cue, dopamine shows an increase in the activity. At the time of the reward which was perfectly predicted, there is no modulation in the activity. Then we can manipulate this experiment at the time after the reward predicting cue. We are basically suddenly not delivering the promised reward, and what we can see is basically a short depression in the activity. And based on this experiment and many other experiments, people basically believe that the activity of these neurons are reflecting a prediction error signal. And basically, then here, for example, reward is perfectly predicted, so what animal is getting and what animal has been predicting are basically equal, and therefore the difference between prediction and reward is 0, and there is no modulation. Here, the difference between prediction, which was 0, and the reward is a positive number, and we see this basically positive prediction error, and the situation is the other way around here. So, in the tasks which have been used essentially for sort of defining prediction error and reward prediction error, almost all of them have been using essentially value-based tasks, either sort of a simple Pavlovian task or a variation of choice task. If you kind of think about the prediction error estimation in the context of a perceptual decision, things are a little bit then more tricky, right? Let's imagine here that, for example, animal is rather than having this sort of very explicit cue, let's imagine that animal is suddenly facing a sort of visual cue which is ambiguous, right? In that condition, animal cannot rely on the learned value in order to sort of make a prediction. Making the prediction in this condition requires an estimation of the confidence that animal has in that each of the choices will turn out to be correct. And so then with this, the question is if this neuron can actually code a sort of prediction error which is suitable for perceptual decision making. Or I can rephrase the question and ask if dopamine responses can reflect value of a perceptual choice. In order to basically address this question, we collaborated with two researchers in Japan, Masamichi Sagakami and Ken Sakunomoto, who were recording from dopamine neurons in this perceptual decision task, which is basically a sort of task that has been very well studied. So animal is initially fixating, there would be a fixation spot, animal is fixating, there would be a random dot task with different coherence in different trials, and after that animal would basically indicate its choice, basically telling us if the dots are going left or right, we basically by doing this saccade, and then animal will receive the feedback, will basically sound feedback for correct and error, and then it will receive basically an outcome. If the animal is correct, the animal will receive a drop of juice, otherwise will be some timeout. Right? And again, given that these guys are super visual animals, the psychomotor function is great. They're doing a great job in basically performing the task. Now, if you want to essentially think about the prediction error in this task, then essentially we can start with the sort of basics of reinforcement learning. We can essentially present each of these events in the task as sort of states, which are coming one after another, and basically facing each of these states, then the model is basically creating a prediction and generating afterward a prediction error. And then the critical state is this one, in which the model is basically facing some ambiguity. And it turned out that sort of in computational sort of reinforcement learning, the way to deal with that is with essentially to construct a belief state, which indicates the probability, the subjective probability that this state essentially belongs to left or right. And that's what we incorporated into a simple reinforcement learning model. So we essentially have two variations of model. One of them big belief state that incorporate a confidence sort of estimation. The other one is a simple reinforcement learning model which only takes into account the average value of the stimuli. And if I train a model like with a medium sort of coherence stimulus, that what we can see is that in the model which has the belief state, we essentially see prediction error for each of these states, and like in the fixation squad, of course, fixation squad is changing the prediction that the reward might come because it caused a prediction error. The feature is that, so in the sort of a stimulus state, what we see in the model with the belief state is the separation of the prediction error size based on the upcoming outcome, which is absent in the standard TDRM model, which doesn't have the belief state. So then we are calling this prediction error decision value prediction error, or DPE, and these are basically a standard TD prediction error. And now I'm going to go through a little bit more detail of the prediction of the model, which are actually very similar to prediction that we showed before. So what we can see here is that in the model with belief state, the prediction error size would depend on the stimulus coherence and trial outcome, both at the time of the stimulus and feedback. And if we separate trials based on the size of the prediction error, we see an improvement when the prediction error at the time of the stimulus is large compared to trials that the prediction error is small. And that is qualitatively different from the prediction of a standard TD model, which shows basically this pattern which I'm showing here. And now I'm going to essentially compare this model with the activity of single neuron that we have recorded in the past. So this is the average activity of neurons when we are essentially aligning the spikes on the stimulus onset. And what we can see here is that at the time of the stimulus, these neurons do have different responses based on the upcoming outcome. Right? It's already suggesting that the activity of this neuron at this time is modulated by the upcoming reward, and it's basically suggesting that the model with belief state will basically work for explaining this data. And that's basically what we are summarizing with the ROC analysis on every single neuron. Right? We can go through the detail of this activity and separate not only based on the outcome, but also outcome and coherence. And the pattern of activity that we see at the time of the stimulus and the time of the feedback is very similar to the prediction of our model with confidence estimation. In this analysis, what we have done is basically to align the spikes on the stimulus onset. And the choice of the animal is happening sometimes around here, right? It's basically making a saccade telling us left or right. So we thought to ask what would happen in the neuronal activity if we align the spikes on the choice, basically saccade, which is for us essentially the first behavioral manifestation of choice commitment. And if we do that, then what we can see is that the activity of this neuron even before saccade initiation is reflecting the upcoming outcome that we can see here in the single example neuron and the population activity. And it's basically extending almost up to 200 milliseconds before saccade initiation. And this is basically telling us that the sort of choice-sensitive responses are reflecting even before choice commitment. Yeah, this is interesting, and this is also something that to me is not specific to this perceptual task. So I have sort of another experiment in which we are basically recording the activity of dopamine neurons in the context of a value-based task. Things are explicit, there is no ambiguity, but the animal is making a value-based task. And if I align responses to the dopamine responses to saccade in that task, I do see the same sort of pre-Sokal or pre-choice activity even in the value-based task. So yeah, then going again through the more detail of this pre-choice activity, we are basically then looking at the activity here, and we can separate trials based on the size of this activity and looking at the psychomotor function of the animal. And what we can see in both animals is that in trial in which the pre-Sokal dopamine is large, the psychomotor function shows improvement compared to other type of trials. Yes, and I think with this I'm going to conclude here, that here we basically had a reinforcement learning model which simply basically included a belief state which is basically taking into account the confidence in the perceptual categorization, and we basically, that model generated predictions, and those predictions, those sort of particular predictions were the sort of signal that we saw in dopamine neural activity. Yeah, so thinking about this dopamine activities, in particular the pre-choice dopamine activity, this is interesting kind of in the context of the current understanding that we have about dopamine. So what we think currently about dopamine is that dopamine is of course involved in reward learning and decision making, but it most probably doesn't have any immediate effect on immediate choice. Rather, it would basically generate this prediction error and correct the valuation and will basically guide behavior through this learning. But what here I show is basically the type of signal which is early enough. It arises basically 200 milliseconds before the choice. And given this time course, this might suggest that, this is more like a speculation, this might suggest that this basically signal has some effect on immediate sort of immediate choice. But this effect is not necessarily in terms of computing choice per se. It might be that this activity is only modulating, for example, the vigor that animal has in basically going left and right. The other thing that I should say about the second part is that as you realize, the type of task that we have here in this monkey experiment is not basically a confidence reporting task. We don't have the sort of baby time or any other measure for confidence sort of report. So what we are showing is not really a neuronal correlate of confidence reporting behavior, but rather we show sort of a neuronal correlate which complies with the computation, with the type of computation which are necessary in order to correctly define prediction error in the context of a perceptual task. And yes, with that I would like to finish and thank Adam, who was involved in both monkey experiment and rat experiment. Zach, Jill, and Alex were involved in the rat experiment. Masamichi and Kensako were involved in the monkey experiment. Wolfram was not directly involved in the monkey experiment, but he had a lot of critical advices. And I should also thank Wellcome Trust for the postdoc fellowship that I have from them. And thank you very much. And any questions, please, be happy.
Thank you. Any comments or questions? Yes, Steve?
So the dopamine responses in the monkeys, it reminds me a bit of the error monitoring literature in humans, where you have this error-related negativity in the EEG signal just around the time of the response.
I see.
And there has been speculation in literature that that signal might reflect dopamine responses around the time of response. And a lot of the discussion in that literature has been on the timing of those signals. And they seem to be very similar to the timing of what you're seeing. So just before the response, just anticipating the response.
Yeah.
And the idea there is that it might reflect some corollary discharge of you kind of realize that you're making the wrong response by knowing what your motor command is.
I see.
So I just thought it was more of a comment just to kind of point out.
Yeah, I wasn't aware of that. So is it something that is it sort of that is? Did you say it's a EEG?
Yeah, so EEG, so error-related negativity.
Okay, I see. Okay. I see.
And it's pretty, it's usually looked at by doing these choice reaction time tasks. And then when people make errors, I see the signal just before they're making the response.
Right, I see. Interesting. Okay. So, yeah.
Yes.
So, so one question: what is the level of heterogeneity in the dopamine response? People tend to basically ascribe one thing to the dopamine neurons, but we know that topographically they also project differently. So, in some ways, what's your thought? Are these neurons encoding the same thing, or neurons that encode different things that project different places, or what's example, there was the heterogeneity in that study.
in this data set.
Yeah.
Okay, so I totally agree. I mean, that's a hot debate in basically current understanding of dopamine. Whether projection specificity can define the function or not is something that like Carl Lazarov and others would advocate, and it is to be probably the case. Yes, I think that's basically the truth, which we can basically evaluate using more sort of powerful method of epigenetic tracing, right? So that I think it will be eventually well studied. So in terms of this data set, so as I showed, like when I was looking at, for example, the single by single sort of single neuron analysis, but like a large portion of this neuron are basically reflecting what I have been seeing in the population activity. But which basically means that probably they are all doing the same thing. But I should say that when you're actually recording from a monkey, and if you are having a particular question, and if you have a monkey which is going to be alive for 2 months, then I think this is a little bit limiting the exploration. So many of the monkey data sets, I think they do see a couple of neurons which are behaving differently, but I do believe that if we explore more, we might see more heterogeneous responses, and that's kind of a limitation which is coming in terms of sort of experimental. But and I also think that several of the studies which have been done and claiming that the responses are heterogeneous are essentially not very well adjusted for behavioral sort of adjustment. Like by simply introducing a punishment, which is an air puff to the face of a monkey, and saying that, oh, look, 30% of these neurons are representing air puff, or not, they are not caring about value or salience. I think that's an interesting thing, but they are only interesting if someone can essentially titrate the amount of that air puff against the reward and actually show that basically it makes sense from the value standpoint. And that's something that Christopher Freelow tried to do in the paper that he published in 2013 in Science. In that paper, he basically calibrated sort of air puff on the face, and what he saw is essentially his claim from monkey sort of data is that there is no representation of, as much as he tried, there is no representation of sort of aversive stimuli in the recording that he had, which is highly in contrast with what Hikosaka published in his group a couple of years before, which showed like a major sort of representation. But I think the way to go is to essentially look at projections and also to define more precise behavioral variables rather than simple category of sort of reward versus punishment is probably a little bit too crude for intelligent animals, I guess.
So I was thinking, so within the monkey task, so the saccade is, it's not like free response. It's not that it can sample the stimulus and then make a saccade at some point. So sort of the experiment is discretized into these events. But do you think you...
So as soon as the stimulus comes, they're free to saccade.
So they can saccade
Yeah,
anytime?
so it's a reaction time task, essentially.
But so do you find this divergence for all responses then? Is it,
Like, you mean the outcome sensitivity?
yeah, there's just to think about whether it was linked to somehow the computation of the decision. So you find this divergence more, so you link it to the, so you time block this to
Okay, maybe
the feedback.
This one? Or this one?
Yeah, so you go back to this one.
Yeah. So I'm essentially just separating.
So so you have saccade at time 0,
Yes.
but that's gonna be, reaction times are gonna be different.
Yes.
Yeah.
That's exactly. So that's basically the onset of saccade, right? And so the other question is if these activities are reflecting the reaction time.
Yeah.
So
Somehow the longer you accumulate, the more you find the divergence.
yes, I did a little bit of regression on that, and I need to remember that now. Okay, so there are two reaction times in this task. The first one is how fast is animal in doing the first fixation, and that was basically like, that's basically giving us one reaction time, and the other reaction time is the choice reaction time. So regressing the activity on the fixation point reaction time was absolutely flat. So the no comment activity was not coding that at all. Regressing the activity on the reaction time of choice reaction time was showing a significant effect. I don't remember how nice was that. That's probably why I don't show.
Longer reaction times.
Yeah.
But longer reaction times are probably going to meet a higher probability of reward. You're going to make the correct decision, more likely.
Okay, so yeah, so the suggestion is to basically look at the binary reaction times and do this analysis, which was there.
If it was related to the choice process.
Yeah,
or
that's
some
a
other
good
probability.
that's a good idea.
I think it gets a little more complicated though. So in the initial moments of sampling, obviously adding additional information gives you a higher probability of being accurate. But then as you filter for the longest reaction times in your data set, you're also filtering for trials where the animal took longer to reach some decision boundary. So typically there are trials with weaker evidence. So
Yeah,
the actual curve looks sort of
but for a given stimulus,
right. Yes,
condition on the
condition on the stimulus.
But yeah.
The internal evidence, of course, will just fluctuate around the stimulus itself.
Chris?
No, I was fascinated by it. So what you're showing is that there's actually there's a dopamine response based on your confidence.
Yes.
But what I find fascinating is this presumably could act as a learning signal
Yes.
in the absence of anything happening in the outside world.
Yes.
Yeah.
Absolutely. Yeah. I'm not sure if it is possible to sort of drive this neuron without any external stimulus. So basically, this is the sort of signal which is coming after a stimulus. So presumably, a stimulus is actually helping the system to essentially start generating a response. But the response is essentially separated before choice. So yes, you're right. We are kind of thinking that this is essentially can have kind of a substrate, a neural substrate for learning from confidence. Essentially.
Because it's in relation to one of Bahadur's experiments, which showed that people would learn in spite of not getting any feedback, particularly if they were telling each other about their confidence.
I see. Okay.
It's an interesting.
But would you ever
fits with that story.
So if you took away the reward at the end, like how, so would this signal die out? There was no reward.
That's a very good question. Those monkeys are dead a couple of years ago, but I can't do that experiment. Yes, I think that before these responses die out, the monkey will stop doing the task. So that's probably the more realistic sort of experimentalist view is probably is that monkey would do probably 2-3 more trials and you would see the responses, but then it would stop. So yeah.
Yeah, I can answer from the human literature. So in human perceptual learning with these kind of tasks, people can learn without feedback, and they also learn almost as well when you give them feedback after the block. So it seems that because this is quite different in terms of learning, whether you have this value learning or this perceptual learning. So it seems that this trial by trial feedback is not necessary to actually do that. So that makes this very interesting.
But can you do sort of like delayed? Can they do delayed reward? So would you be able to learn some association? If I for this long period of time do well, then something good would happen.
Yeah, you mean they can do this task?
Yeah, so if you
Yeah.
have trial by trial feedback, but there's some accumulation that's happening in the background.
Yeah, so in Bootcamp lab they did an experiment which they actually published this year in Nature Neuroscience, and that is a task which is reminding me about your question, and that is a condition that monkey can actually accumulate reward across trials with some interest rates, right? And they are able to do that. So these monkeys, it's actually an experiment that we did many years ago, but it was published now. And this is essentially the monkey is rather than getting the reward, he would say, no, I'm going to keep the reward for the next trial because there will be some interest rate in that. So I will collect more, and they are able to keep this in mind for up to, I think, from the data, 7-8 trials sometimes. And yeah.
But it was just to see if you could find some learning signal in the absence of immediate rewards.
Yeah. Yes, it is a question. I don't know how how it is possible to motivate an animal without an outcome to perform enough trials for you, and basically, to do the analysis. And I think there is also a danger in that experiment that a monkey, you see sometimes that monkeys are even if you are careless and the juice spout is off for let's say for a couple of trials or 5 trials, they would actually do that. But then I would actually usually think of that as sort of a monkey which is just not properly engaged, and he has been so well trained that he's taking the experiment as more like a habit and not really caring about the outcome, but rather just being bored in the cage and coming here to basically do something else. So I think it's a very tricky thing to I think that it's very tricky, sort of experimentally very tricky to have an animal engage without the reward. Unless you have other type of reward which are
Yes. But these waiting manipulation experiments are quite interesting, and would be great to have more experiments in humans with this very
yes.
like we talked about. And but I guess if we did this in humans, then pupil dilation would predict how long people would wait anyway, wouldn't it? If you
so I mean it's
basically the same model.
Can you just tell me in the break about something you did in humans?
Yeah, I have
On this?
a large data set with several human subjects, in some cases tens of thousands of trials in individual subjects, performing the psychometric discrimination test using Poisson clicks. So we can align to the moment of choice, look back at the history of evidence and see how that contributes to confidence, as well as all of these other parameters like reaction time and discriminability, and how long the subject will invest their time in the belief they were correct. So
It would be great if you could share some of this in the discussion.
yeah, sure.
But in fact, there's a paper floating around somewhere trying to get published by Sid Critter and his group in Paris, who've used waiting time with infants. And that works extremely well.
And they're looking further.
No, so they see 2 boxes, a toy is put in one box, the curtains are closed, then they're opened after a delay, and they have to point to which box.
An infant.
And they're allowed to feel inside, and of course there's nothing there anymore, and they feel longer. They show exactly this nice.
Oh, I see.
They feel longer when they're more confident.
It's quite interesting. But it's not. You
Not
can't
published.
publish it.
It's been presented in conferences.